NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math tutorial video. Today we'll be simplifying a radical expression step by step. Let's look at the following problem. Let's start by separating the negative sign. When we have a negative value raised to an even power, the result is always positive. Since our exponent 6 is even, negative raised to the power of 6 becomes positive. This is because negative times negative gives positive, and with an even number of multiplications, the final result is positive. Now, we need to handle the exponent. When raising a radical expression to a power, we can apply the power to the radicand, and then simplify according to the power of a power rule. When a radical expression is raised to a power, the power applies to the entire expression. Let's continue by simplifying the exponent inside the radical. We'll apply the exponent to the radicand using the power rule. We have a to the power of 4, and that is raised to the power of 6, so we get a to the power of 24. This is based on the power of a power rule, where we multiply the exponents. Now let's separate out as many powers of 7 as possible from the exponent. We can break down 24 as 21 plus 3. 21 is divisible by 7, as 21 equals 7 times 3. This allows us to rewrite our expression in a cleaner form. Now, let's look at a to the 21. Since 21 equals 7 times 3, we can extract a to the power of 3 from under the radical sign. This is a key rule of radicals. If the exponent is divisible by the index, we can extract that factor outside the radical sign. Welcome to today's mathematics lesson, where we'll explore an important property of nth roots. This property is fundamental in algebra and helps us understand how roots and powers relate to each other. Let's begin with an example. Take a look at these formulas showing the relationship between nth roots and their original values. First, with square roots or second roots, we can see that the square root of a times the square root of a equals a. For cube roots or third roots, the cube root of a times the cube root of a times the cube root of a equals a. This pattern continues. And in general, for the nth root, if we multiply the nth root of exactly n times, we get back the original value, a. Let's explain this rule more formally. The rule states that when we multiply a radical expression by itself a specific number of times, we get the value inside the radical. Let's use a specific example to make this clearer. Consider the square root of 9. We know that the square root of 9 is 3. So, the square root of 9 times the square root of 9 equals 3 times 3, which equals 9. This confirms our rule. When we multiply a square root by itself, we get the value inside the square root. Now, let's look at a cube root example. Remember, the cube root of a number is the value that, when cubed raised to the power of 3, gives the original number. The cube root of 8 is 2, because 2 cubed equals 8. So, the cube root of 8 times the cube root of 8 times the cube root of 8 equals 2 times 2 times 2, which equals 8. This again confirms our rule. When we multiply a cube root by itself 3 times, we get the value inside the cube root. Let's visualize this concept geometrically to deepen our understanding. For the square root, we can think of it in terms of the side length of a square. If a square has an area of a, then each side has a length of square root of a. Similarly, for the cube root, we can think of it as the side length of a cube. If a cube has a volume of a, then each side has a length of cube root of a. This gives us a geometric interpretation. The nth root of a number represents the side length of an n-dimensional shape, whose measure, area, volume, etc. is the original number. Now, let's examine the general rule algebraically. The nth root of a can be written as a to the power of 1 over n. When we multiply this expression by itself n times, we're effectively adding the exponents, which gives us a to the power of n times 1 over n, which simplifies to a to the power of 1, or simply a. This provides an algebraic proof of our rule. Multiplying the nth root of a by itself n times equals a. Let's try a practice example. Quick challenge. Calculate the fourth root of 16 and verify our rule by multiplying it by itself 4 times. First, we need to find the fourth root of 16. The fourth root of 16 is 2, because 2 raised to the power of 4 equals 16. Now let's multiply the fourth root of 16 by itself 4 times. 2 times 2 times 2 times 2 equals 16. This confirms our rule yet again. multiplying the fourth root of 16 by itself, 4 times gives us 16. Let's summarize what we've learned today. Welcome to our math tutorial on the properties of nth roots. In this video, we'll explore how to evaluate nth roots for different types of numbers and understand the rules that govern them. Let's start with our first rule. If m is a positive integer and it equals 0, then the nth root of a raised to the mth power equals 0. Symbolically, this means that the nth root of 0 raised to the mth power equals 0. Now, let's move to our second rule. If the nth root of a is defined, then we can write the nth root of a raised to the nth power equals a. For example, when we have the cube root of 8, we can cube both sides to get 8. However, not all expressions involving roots are valid. For instance, the equation square root of -2 squared equals -2 is not valid because the square root of a negative number is not defined in the real number system. Now, let's establish a general rule for nth roots. When n is odd, which means n equals 2k plus 1 for some integer k, the nth root of a is simply a. When n is even, which means n equals 2k for some integer k, we need to consider whether it is positive or negative. If it is positive, the nth root of a to the nth power equals a. If it is negative, the nth root of a to the nth power equals negative a. Let's look at some examples to better understand these rules. First, the fourth root of -3 to the fourth power equals 3. This is because n equals 4, which is even, and it equals -3, which is negative. Next, the fifth root of 32 equals 2. We can verify this by noting that 2 to the fifth power equals 32. Finally, the seventh root of -2 to the seventh power equals -2. This is because n equals 7, which is odd. Let's summarize what we've learned about nth roots. When it equals 0, the nth root of a to any power is 0. When n is odd, the nth root of a to the nth power equals a. When n is even and it is positive, the nth root of a to the nth power equals a. We want to evaluate the square root of the quantity x squared minus 1, all squared, when x equals 0. Let's solve this step by step. First, we'll use the substitution rule to replace x with 0 in our expression. Now, let's calculate 0 squared. 0 squared equals 0. Next, let's calculate 0 minus 1. 0 minus 1 equals -1. Now, let's calculate -1 squared. Remember that when we square a negative number, we get a positive result. So -1 squared equals +1. Finally, we take the square root of 1. The square root of 1 is 1. Let's move on to our second example. Now we want to evaluate the same expression, the square root of the quantity x squared minus 1, all squared, but this time with x equals -2. First, we'll use the substitution rule again to replace x with -2 in our expression. Now, let's calculate -2 squared. Since -2 squared equals +4, we get square root of quantity 4 minus 1, all squared. Next, let's calculate 4 minus 1, which equals 3. Now, we need to calculate 3 squared, which equals 9. Finally, we take the square root of 9. The square root of 9 equals 3. Let's summarize what we've learned. When evaluating expressions with nested squares and square roots, we follow these steps. First, substitute the given value of x into the expression. Second, evaluate the expressions inside parentheses, working from the innermost outward. Third, handle exponents and radicals according to their rules. We've seen how this works with two examples. When x equals 0, the result is 1. When x equals -2, the result is 3. Remember that squaring a negative number gives a positive result, and the square root of a perfect square is simply the positive value being squared. Our first example is to evaluate the expression square root of the quantity x squared minus 1, and then the whole expression squared, when x equals 1. Let's solve this step by step. First, we substitute x equals 1 into our expression. Now, let's compute 1 squared minus 1 inside the parentheses. Let's simplify 1 minus 1, which equals 0. Now, we square 0 to get 0 squared. And finally, we take the square root of 0, which equals 0. Now, let's solve our second example. We have the same expression, but this time x equals square root of 2. Let's start by substituting x equals square root of 2 into our expression. Now we simplify the square root of 2 squared, which equals 2. Next, we calculate 2 minus 1, which equals 1. Now we square 1, which equals 1. Finally, we take the square root of 1, which equals 1. Let's summarize what we've learned. We evaluated the expression square root of x squared minus 1 squared for two different values of x. When x equals 1, our answer is 0. When x equals square root of 2, our answer is 1. We followed the same step-by-step process of substituting the value, performing operations inside parentheses, squaring the result, and then taking the square root. We need to evaluate the expression when x equals negative square root of 3. Let's solve this step by step. First, we'll substitute x equals negative square root of 3 into our expression. Next, let's simplify the square of negative square root of 3. Remember that when we square a negative number, we get a positive result. Now we can compute 3 minus 1, which equals 2. Next, we square 2, which gives us 4. Finally, we take the square root of 4, which gives us 2. Let's move on to our second example. Now we need to evaluate the same expression when x equals 4. Again, we'll solve step by step. First, substitute x equals 4 into our expression. Next, let's compute 4 squared, which is 16. Now we calculate 16 minus 1, which equals 15. Next, we square 15, which gives us 225. Finally, we take the square root of 225, which gives us 15. Let's do one more example. This time, we'll evaluate the expression when x equals 0.1. As before, we'll substitute x equals 0.1 into our expression. Let's compute 0.1 squared, which equals 0.01. Now we calculate 0.01 minus 1, which equals negative 0.99. Next, we square negative 0.99. Remember that squaring a negative number gives a positive result. So, negative 0.99 squared equals 0.9801. Finally, we take the square root of 0.9801, which gives us 0.99. Let's analyze what's happening in our calculation. When we evaluate the expression square root of quantity x squared minus 1 squared, we're essentially finding the absolute value of x squared minus 1. This is because squaring a number and then taking the square root gives us the absolute value of that number. So our expression is equivalent to the absolute value of x squared minus 1. Let's summarize what we've learned. We evaluated the expression square root of quantity x squared minus 1 squared for three different values of x. 4x equals negative square root of 3. We got 2. 4x equals 4. We got 15. 4x equals 0.1. We got 0.99. We also recognized that this expression is equivalent to the absolute value of x squared minus 1. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.